Hello, welcome to Real Learning Center. So today we are going to start basically a new topic which we call oscillations and waves. So they are very closely related, the oscillations and waves. So let's cover them in two sessions. The first one being basically trying to understand what is a string and what is a pendulum. Okay. The second one being trying to understand what is a wave and a little bit of sound waves. So that's what we are going to cover in the two sessions. So let's start with basically what is oscillation. We have heard this word oscillation. We have heard this word vibration. So what is this vibration and what is this oscillation? So one simple way to say is basically back and forth motion of anything over a central point. Back and forth motion of anything over a central point. You can see this pendulum. It goes like this, and let us take its middle point as a center point, the same point. From there, it goes to the other side and comes back. Goes to the other side and this side and comes back. So that basically is nothing but an oscillation. And even in the spring, you can see actually in the spring, there is a middle point. Let us say is the central point, the B point. It goes up and comes down. Comes to the middle, goes up, comes down. So that is basically there is a central point over which, around which it goes. There is a displacement up and down. Okay, so that is basically called an oscillation. So back and forth motion over a central point is an oscillation. Okay. So now what is the vibration? So vibration is simply a high speed oscillation. You see here in a string, the string is really oscillating, but it is so fast oscillating that I can't see them going up and down, and we see a kind of a blurry picture. And even a string, if you take a string of a guitar or a veena, so you can clearly see that these strings actually vibrate. So we don't say oscillate, because it's the same as oscillation. It's just that when it oscillates at a slightly higher frequency for us, we call it as vibration. It's a common term, vibration. So we can interchangeably use these words, vibration and oscillation. So now, I would like to give a slightly more an abstract definition of what is called as oscillation. Yeah. Let us see whether we can actually understand that abstract definition. So the abstract definition is this: the oscillation is actually the repetitive variation, typically in time, of some measure. Look at this. The abstraction that we get out is this: oscillation is a repetitive variation. We didn't say displacement. We say repetitive variation. So what is the meaning of that? In the case of a displacement, position is repetitively varying. Okay. It could be something else. For example, pressure, air pressure may be repetitively varying. In which case, we don't call it as a displacement. We have to call it as repetitive variation. And the variation is generally across time. That like it is going in terms of time. Now this much, a little bit later, this much more, a little bit later, this much more. So we use time. Okay. So however, it is written as typically in time. What is the meaning of that? That means it is not always. Sometimes it could be in terms of space or something else. For example, assume that there are people standing. Okay. And when they are standing, one of them is, let us say, 6 foot height. The next guy is 5 foot. Next guy is 4. Next guy is 3. Again, next guy is 4. Next guy is 5. Like that they are standing. So you can clearly see that there is a 6 to 3 and up to 6 there is a variation. Okay. And this variation is a kind of oscillation of height. Okay. So, but not in time, but in space. If you go along space, you can see that it varies. So even that is a kind of oscillation. So, but however, typically oscillation word brings us only the time into our head. Okay. Of some measure. That means, as I talked about, it need not be just the displacement or a position. It could be anything. Temperature variation over days. Today it goes, let's say 30 degrees. Tomorrow 31, 32, 33, 35, back to 34, 35, 33, 32, 31, 30. Like that, if it keeps varying every day, we say, oh, temperature is oscillate between 30 and 30. So this is basically in an hour you can change in time, you can change in hours, days, whatever. So over time, typically some measure is changing, so we call it as oscillation. So about a critical value, it may be in the middle, say about a central value, some central value is there around which it is moving, or often a point of equilibrium, we call it as equilibrium. The middle value is called equilibrium. Or sometimes we don't worry about the equilibrium, we talk about two extreme values and it is going between. It's also called oscillation. So oscillation, now we have given a definition which is a little more abstract, because this definition will give us an ability to define waves which are not just mechanical. We will see what they are. Okay. So the oscillation here is basically the repetitive variation, typically in time, of some measure about a central value or equilibrium point. Okay. That is basically called oscillation. So now let's look at some of the basics of oscillation. Okay, oscillation basics. We have here with me basically one pendulum which is going oscillating. Okay. Now when it is oscillating, that pendulum, you can clearly see that it is going from P to Q to R, back to Q to P, keeping on doing that. So what I will do is that I will actually look at what is the maximum displacement. The maximum deflection in this case is actually angle theta. Yeah. Maximum deflection is theta and maximum displacement is A. Yeah. So A is from where it has been. So either the maximum deflection or the maximum displacement, we call it as amplitude. In various circumstances, we call this one or this one as amplitude. And then we're just basically developing a language around the oscillation. So one of the important words is amplitude. Next, let us look at basically time period. What is the time period? Time period is nothing but time taken to go from P to R through and back to P to R, back to basically the total time. What I'm going to do, I'm going to wait till it comes to P, look at my watch and find out how many seconds it takes to come back to P. Okay. So sometimes it may not be very difficult to measure just one oscillation. Instead, I will measure basically 20 times going under and later divided by 20. So I can calculate per hour. So basically for one full cycle, going and coming back is one cycle. For one cycle, whatever time it takes, we call it as time period. Okay. And then, if you take, for example, one more such a pendulum, we can clearly see the other pendulum is actually longer than the length of the pendulum is more. And because the length is more, you can see its period is varying, in the sense that it is going more slowly than the other. The length is smaller in the first pendulum and it goes quite fast, and the length is slower in the second one, it goes slowly. So that means basically time period is actually dependent on the length, and when length increases, the t increases. The length is dependent on it. So there is actually, if you go and change the mass, for example, if I make it a bigger, these are the experiments that you can do. If you actually make it mass bigger, then it doesn't change the time period. It still remains the same. Only if the length changes, it changes. And there is one more parameter which changes the time period. What is that? You can see, look at the formula for the time period will come to. T is equal to 2 pi into root of L by G, where L is the length. We are very sure. When length changes, time period changes. You can see it. So the by G is actually the acceleration due to gravity. So acceleration due to gravity doesn't change on R. So only L is a parameter. L changes. But on the other hand, if you take actually the same pendulum and go to moon, where the G changes, when G changes, what happens? G slows down. If G is less, T is more, because it is in the denominator. If which means that in moon acceleration due to gravity is 1/6 of Earth. So what happens? There the time period also substantially increases. T is equal to 2 pi root L. Slowly. Okay. So the if you look at basically the pendulum clocks that we used to have, the tick clocks, there they used to design the length in such a way that the exact time period on Earth when it is done is 1 second. In fact, this will be a small exercise for you guys. T is equal to 2 pi root L by G we have. You keep T is equal to 1 second and find out L for the given G. Okay, G is 9.8. So find out L. Then you will know what is the length of a pendulum to give us 1 second tick. So the same pendulum clock will not work if you take it to the moon because it goes slow. Okay. So that is basically the basics of oscillations. So now there is one more parameter which we call frequency. That means how often it is oscillating. In a sense, in 1 second, how many oscillations? In 1 second, if twice it goes and comes, F is equal to. So we measure that in terms of hertz or cycles per second. So in 1 second it only goes half time. Means in 2 seconds it goes once. In which case we will say frequency is half hertz. Okay, it is possible that frequency can be very high, 100 hertz, 200 hertz, 500 hertz, kilohertz, megahertz. So not for the physical pendulum. This kind of a pendulum can only be in some few hertz. Okay. Now, so once you understand the concept of frequency, now you can have a relationship between frequency and time period. So time period and frequency are reciprocal in the sense that time period is equal to 1 by frequency and frequency is equal to 1 by time. So to solve any problem, these things will come in handy. Given time period, you can calculate frequency and frequency. Yeah, this is basically fundamentals of oscillations. Now, even the same thing is true in spring motion. So you take for example this is spring. Okay, I am placing the spring with a mass on a surface which is very means no friction. In such a surface, what will happen is it will not slow down, it will keep on happening. So the maximum displacement I am calling A and minimum this side also minus A. So this also we basically nothing but similar to the motion of the pendulum, where it goes on one side and comes back. And generally in spring motion, we also realize that the displacement when it happens, it actually, the more the displacement, higher the restoring force. It wants to get back. So that is why we say F is proportional to the displacement. F is equal to minus kx. That is one of the rules of a spring motion. Okay. So more the displacement, more trying to come back, more higher. Okay. So this is the spring motion that we talked about. And if you look at basically tuning fork, for example, okay, we talked about a tuning fork. Tuning fork is something which vibrates when you hit it. So the way it vibrates depends simply on the length of the tuning fork. The lengthier tuning fork vibrates with lower frequency. The frequency is now heard. You can actually keep it to your ears and hear the frequency. You get a sound of the tuning fork. So if this length is smaller, tuning fork, you will have a higher frequency. You get a higher pitch. If the length is bigger, longer, then you will have slightly lower pitch. Okay, so higher pitch is like lower pitch is like so like that. So this is basically how a tuning fork you can see is similar to the pendulum. Because pendulum you can clearly see the vibration, oscillation. In tuning fork it oscillates so fast that we call it as vibration. The tuning fork that you are seeing there on the screen actually vibrates at 512 hertz. Means it will actually vibrate 512 times like this in a second. So that's why we can hear. So that's a sound. So bigger objects always vibrate slow and smaller objects always vibrate fast. So that is one of the most important learning from the vibration. So let's check our understanding on what are the things that we have learned. The first question is, time period of the pendulum depends on. So I hope you can answer this. Is it depending on the amplitude, or is it depending on the mass, or it is depending on the length? You can do an experiment on it. In a pendulum, instead of actually pulling up only this much and leaving it, it will do that. Pull it this much and leave it. Do that. In which case will the time period increase or not? So we have increased the amplitude. So you can check yourself and let me know what is the answer. Okay? Next question is, if you take an oscillating pendulum to move, what will happen to its time period? Will it increase or decrease? Look at the formula. T is equal to 2 pi root L by G. You should be able to answer this question. So we have now understood basically a little bit basics on what are oscillations and how do we deal with string and pendulum based oscillations. So the next session we will actually talk about the wave basics and also move on to a little bit on to understanding the sound wave.